great pleasure to, it is great pleasure to welcome Xiaodong Xu from University of Washington to give a talk at RCQM. Xiaodong actually, I know Xiaodong's work from our earlier neutron scattering on chromium triiodide. So I read a lot of his pioneer work on the cleave single layer on chromium triiodide and various other materials. So today he's going to talk to us about the spin charge and lattice coupling effect in van der Waals crystals. Yeah, it's all yours, Xiaodong.
Thank you, and thanks, Pengcheng, for the invitation. And as Pengcheng mentioned, right, today I'm going to talk about the spin charge and lattice coupling effects in these van der Waals crystals. I think there's a lot of opportunity there actually to study the interplay between different degrees freedoms in these van der Waals materials. So today I'm going to cover two topics. So I'll start with the zigzag antiferromagnetic nickel phosphate trisulfides, and in this system I will show you the coupled excitons, zigzag magnetic order, and also phonons in these systems. And in the second part of my talk, I will also discuss these Moiré magnetisms in twisted chromium triiodides. And in such a system, we'll also see very interesting spin lattice coupling effects from the layer stacking effect. Okay. So before I go into my talk, and here's just the acknowledgement of the people who have done this work. So the first part on this zigzag antiferromagnet is mainly done by graduate student Cao Huangpo and my former postdoc Qi Zhang, and with collaborations of my colleague at the UW who grow these bulk crystals. And we also have ongoing collaborations with Haidan and with New Gallic, use these electron diffractions and ultra-fast pump probe technique to study these material systems. And the theory is done by my colleague Di Xiao. Now he's at the University of Washington, just moved, and also Wang Yao at the Hong Kong universities. So in the second part of my talk, right, and the Moiré magnetism work is mainly done by my former graduate student Tiancheng Song and my current graduate student Eric Anderson, in collaboration with Qi Sun. He's a postdoc at the York Retrieval Group at the University of Stuttgart. So this work is really equal contribution from these two groups. We also has crystals from HBM from the famous Japanese group, and the bulk crystal chromium triiodide is from my longtime collaborator Michael McGuire at Oak Ridge National Lab, and also my colleague Di Xian Ting Tao, right, the usual suspect, provide the theoretical support. Okay, so let's start with nickel phosphate trisulfide. So the motivation for us is to identify, magnetic, right, van der Waals semiconductors or insulators with a strong correlation effects. So with the available of this type of material system, then we're gonna apply is conventional, right, 2D material technique, such as electrostatic controls, heterostructures, string engineering, Moiré pattern, etc., to study these excitonic effects in these magnetic semiconductors. So such a platform, right, will open up opportunities for these photo spin physics, and also has promising some technology application like optical spintronics, etc. So the material I'm going to talk to you today is MPX3, which is transition metal, phosphorus tricotonite. And the metal M here can be nickel, manganese, or iron, and the cotonite X can be sulfide or selenite. So this actually it's a really rich, it's a class of material with really rich properties. Just one example, what I really like is, for example, say iron phosphate triselenite, and there's been a lot of study in this material system. It itself is a zigzag antiferromagnet, but under hydrostatic pressure, there's a phase transition from this magnetic order actually into a superconducting order. So what you're seeing here, just a resistance measurements, right, of these crystal as function temperature. So at the high pressures, right, there's a superconducting transition. You can see that the resistance drop to zeros with the critical temperature on the order of 4 to 5 Kelvin. So this is you can see from this a simple example, right? You can already see that the material system has a strong correlation effects. So this class of material MPX3 belong to these honeycomb lattice, and we can look at the Heisenberg model, which used to describe the magnetic interactions in these honeycomb lattice. So here I show 3 terms here in the J1, J2, and J3. So J1 represents the first, right, the nearest neighbor exchange interactions, as I show here. And the J2 is the second nearest, and the J3 is the third nearest exchanging interactions. And it depends on the ratio of these J1, J2, and J3. The system can behave very differently in terms of a magnetic order. So my collaborator Dixiao, he calculated the phase diagrams as function ratio of J1, J3, and also J2, J3, showing these plots here. So for example, right, in this bottom left corner, we'll get the ferromagnetic order. So what it means is all the electrons spin going to point into the same directions. And also on the bottom right corner, and this is a new order. So what it means is, right, the adjacent lattice has a spin pointing into exact opposite directions. And in the middle is interesting, is also a new order, but it has a different type. For example, right, you can have a zigzag antiferromagnetic order. So what it means is in the zigzag directions, the spin is aligned, but in the adjacent the zigzag spin chain, the spin is aligned in opposite directions. And in this little corner, you can also get a stripy order. So basically the spin is aligned in these armchair directions, but aligned oppositely in these adjacent armchairs. So for the for this MPX3, this family of materials, and they actually has a pretty rich magnetic order. So for example, for this iron phosphotrisulfide and nickel phosphotrisulfide, they belong to these zigzag antiferromagnetic orders. And for the manganese phosphotrisulfide, right, actually it's new orders. So this is just a brief summary, right, of these three materials. I'm going to mainly talk about these nickel phosphotrisulfide in this talk, but we'll briefly mention iron phosphotrisulfide and also manganese phosphotrisulfides. So for nickel phosphotrisulfide, it's a 2D and a subtropic Heisenberg magnets. And for the iron phosphotrisulfide, actually it's Ising order with this new temperature 120 kelvins. And for the manganese phosphotrisulfide, actually it's a new order, and it's a 2D, can describe by these 2D Heisenberg spin interactions, and with new temperature about 78 kelvins. So let's start with the focus of the first part of my talk, which is nickel phosphotrisulfide. And here I show the the spin structure in the top view. Right, you see all the spin is aligned in this direction, we define as A, and orthogonal to this zigzag direction, which is B. And if I look at from the side view, the spin is mainly aligned in the plane, but the recent neutron scattering study also shows that the spin has a slightly tilted angle out of plane. And this still, I think, ongoing study. It's not settled. But for this talk, we can basically consider the spin is aligned in the plane here. Okay. And there are already a lot of work done in a bulk crystal for nickel phosphotrisulfide. For example, here, right, this work studied the magnetic susceptibilities as function of a temperature, and then you can clearly see the magnetic phase transitions happen about 150 kelvins. And then we'll go back to this particular data a little later. So there are also optical study being done in this nickel phosphotrisulfide, and in this particular work, they study the optical conductivities, right, as function temperatures, and they observe three resonance peaks called A, B, C. So A, B, C, generally they attribute to these charge transfer excitons. So what's interesting in this work is they observe the exciton outside strength transfer as the temperature below the near temperatures. So from here, the paper basically concluded there's a strong coupling between these electronic degree freedom and also spin degrees freedoms. And there's another work studied the Raman spectroscopies of nickel phosphotrisulfide as function of layer thickness. So in this work, they found there's a Raman mode exhibits a splitting when the temperature is below the new temperature. So they measure this, the Raman mode splitting as function of a temperature. So what is, as you show here, right? And they found this, above the new temperature, the splitting vanishes. So this particular splitting can be used to measure the magnetic orders. So what they found is this splitting exists all the way to bilayer, but it vanishes for the monolayer. Okay. Then what this work indicates is, well, at the monolayer limit, it's possible to study these BKT transition from the XY models. So all this work shows there's a quite interesting magnetic interactions and the possible couplings between the electronic degree freedom and the spin and the lattice degree freedom in this nickel phosphotrisulfide. So my lab is focused on the optical spectroscopies, especially we're interested in the exciton physics. So the first thing we do is we just measure the luminescence and luminescence from these thin bulk nickel phosphate trisulfide. Before we basically tried quite a few different materials, and you know, this is the one actually show really nice exciton luminescence. So first of all, you see here is a really pronounced luminescence at around 1.475 EVs. Okay, basically 40 nanometer. The measurement down at the temperature of 15 kelvins. The first thing really get my notice is the Linewidth. So Linewidth of this peak is really narrow. Only it's 350 micro EVs. So what I mean is narrow. Okay, so let's make a comparison, right? And the other type of 2D semiconductor we know, for example, like TMDs. So this is the state of the art of a monolith MS2 sandwiched by boron nitride. And as you can see, the Linewidth is on the order of 4 million EVs, right? So it's about the order of magnitude larger than what we're seeing here in nickel phosphate trisulfide. And we can also compare it to the exciton in state-of-the-art gallium arsenide systems. So Linewidth is on the order of a 0.5 milli EV scale, so slightly larger. So that's what I mean. It's kind of remarkable. We basically exfoliate these crystals and measure luminescence. We see such a luminescence with such a narrow Linewidth. So the second thing caught our attention is the very strong anisotropy of the systems. So right in this spectrum, you see two curves, right? One is red, the other is blue. So red is basically we perform these linear polarization result measurements. The red means that the polarization along these is a V. It's along the B axis, orthogonal to the zigzag train, and the H is along the zigzag train. So you can see that the polarization, right, of the light, the luminescence, is strongly polarized in these vertical directions. Okay, so that's what I mean. Yes, I may misspell, but anyway, so the polarization is strongly polarized, right, orthogonal to the zigzag spin trains. Okay, so this already indicates, right, these degree of polarization, that this optical anisotropy somehow is connected to these magnetic orders. So we can perform temperature-dependent measurements. On the left side, you see these luminescence, right, as function temperature from all the way 15 Kelvin to 160 Kelvin. So this is two things stands out, right? The first is the peak gets much broader, above 100 Kelvins. And the second is the intensity really drops, and the signal basically vanishes about 150 Kelvins. So this data already suggests the luminescence has strong connection to the formation of zigzag antiferromagnetic order, but also the Linewidth of PO and also intensity, right, has a the origin of these has some complicated effect. For example, temperature, like phonon effects, can also affect the Linewidth and intensity, etc. So so the quantity actually we can really look at is the degree of linear polarizations, as I show here. So basically, the intensity of a vertical polarized light minus the horizontal, and then normalized by the sum. So we plot this degree of linear polarization as function temperature, and it has this behavior, which is shows the degree of linear polarization almost vanishes above nil temperature. Okay. And we're not the only one observe these phenomena. So there's a work from Boston College. They also observe very narrow luminescence from these nickel phosphate trisulfide. Basically, the data is consistent with us. That's really good. And they also observe the degree of linear polarization also drops, right, as function temperature, and all consistent. So there's another work from a group at Korea. They in this work they also observe a narrow external luminescence as function of layer thickness. They measure all the way to the trilayer, and they didn't observe the luminescence from bilayer and the monolayer. And the second is they also measure the peak Linewidth of temperature, just as I show you, right? The Linewidth is actually broadened as the temperature increases. So an interesting point made by this paper is they attribute this exciton to a mini body exciton. So what it means is a John Wright singlet. So the evidence is mainly coming from the recent X-ray scattering measurements, which is actually beyond what I can stand. But if you're interested in this topic, you should check out this paper. Okay, so but all this work, we see this the exciton, right, has signatures they connect to these main order, but where these optical anisotropy really coming from? So address this question. So what we did is we found this paper, and this paper measures the magnetic susceptibility anisotropies along these A axis and also B axis, right? A axis is along the zigzag spin train and the B is orthogonal. So you can see that the magnetizability, right? In plane magnetizability, which is for along the A and the B axis, initially was equal to each other until below the new temperature, then start to deviate. So we took this data from the paper, then we extract, right? We take the difference of the magnetizability along this A and the B axis, so plot it as function temperature. So these are the data we basically extracted from this paper and calculate. We got it from the left plot. So you can see that these in-plane magnetizability and anisotropy is really the order parameter, right? It's a 0 below the new, above the new temperature and start to increase below the new temperature, okay? Then we can plot, overlay these degree of linear polarization in the PL, which is blue dots, and with these in-plane magnetizability and anisotropy, right, in these red dots as function temperature. Now you can see that the degree of linear polarization resembles these order parameter, right? So you can say that, well, this is strong evidence. We do have these exciton coupled to these zigzag antiferromagnetic order, and the optical anisotropy is coming from these zigzag magnetic orders. Okay, so another, usually the interesting feature arise with in layer material, which is layer dependence, right? So we also perform these exciton luminescence measurements as function of layer thickness. The intensity, the plot I show you here, just PO intensity map as function of layer thickness. You already see that the signal drops dramatically from these 7-layer to 4-layer, 3-layer. In the 2-layer, basically see nothing. So you can just extract the spectra as function of layer thickness and plot it here. So from the thin bulk all the way to trilayer, you can see that the PO intensity drops, okay? But what's really dramatic is from trilayer and until the bilayer, the PO intensity decreased by an order of magnitude. And then from the bilayer to monolayer, basically we don't see anything come out from the samples. So this data basically indicates, right, there's some kind of electronic structure transitions from trilayer to bilayer and then bilayer for monolayer, okay? And we can also extract the peak intensities and the peak positions as function of layer thickness, as shown you here. So the data shows that as we reduce layer numbers, and there's a blue shift of these exciton luminescence. So there's a few points we can take from these measurements. First of all, right, there's no PL signal in the monolayer, and this indicates, right, there's electronic structure transitions from thin bulk all the way to monolayer. And then also we see the exciton signal, right, has a strong layer dependence in terms of intensity, in terms of the energy. So this means that the exciton wave function actually is not highly localized. It depends on the interlayer couplings, right? So this is a one-year-like type characters for the excitons. Okay, so at the time when we had our results and wrote up the paper, so we also found there's a theory paper online and eventually published. So this paper, this theory, this basically is a DFT calculations, already report the thickness dependent electronic structures and the optical properties in these nickel phosphide trisulfide films. So basically found that the optical anisotropies and the electronic structure, etc., has a strong layer dependence. I'm not going into details of these calculations, but basically what I present to you is the calculation done by my collaborator, and essentially similar to what's published. And here I show you the band structure calculated from these density functional theories. And then in the monolayer, right, we found these valence band maximum and the conduction band minimum is not in the same key point. So basically, right, they're far away from each other in the momentum space. So that's a indirect band gap semiconductor. So this is the reason, right, we don't see any luminescence in the monolayer. Now, just go to bilayer, and the calculation shows that right, you see this band is already lower down. And this energy near degenerate with the lowest energy of conduction band. So this point in the momentum space is still, distinct, right, from the valence band maximum, but the difference is smaller. So this facilitates a little bit of luminescence in the bilayer. Then as we keep increase the layer thickness, we found that this point at the conduction band becomes the lowest energy minimums. And this is the reason we see stronger luminescence as we increase the layer thickness. But overall, the material itself is still indirect bandgap semiconductors. And this also explains why when we lower the, reduce the layer thickness, we see blue shift of the exciton luminescence, because these little, the band edge, right, of these conduction band actually, right, the energy increases as we reduce the layer thickness. Okay, so this calculation is consistent what we observed from these luminescence measurements. So now what I show you is we have these the zigzag antiferromagnetic order, and introduce a strong optical anisotropy. Then these optical anisotropy can also be measured through linear dichroisms. So in the linear dichroism measurements, so what we get is we send in linear polarized light, and then we measure the optical reflectivities. And here's the data. We measure this linear dichroism, right, from 3 different crystals: iron phosphate trisulfide, nickel phosphate trisulfide in blue, and also the black dots represent manganese phosphate trisulfides. So basically, we measure normalized reflectivity as function of the incident and polarization angles. And clearly, right, the data shows that for both iron phosphate trisulfide and the nickel phosphate trisulfide has a strong optical anisotropies, right? And but for the manganese, it doesn't show any optical anisotropies, doesn't show linear dichroisms. So this is consistent, with their magnetic order for both iron phosphate trisulfide and also nickel phosphate trisulfide. It's a zigzag antiferromagnetic order. So these zigzag antiferromagnetic order breaks the rotation symmetries and give rise to these optical anisotropies. But for the manganese phosphate trisulfides, it's a new order. So the 3-4 rotation remains. That's why we don't have these optical anisotropies. So from a symmetry point of view, right, all the data is consistent with the magnetic orders. Now with these linear dichroisms, we can perform a spectroscopy. So here I show you linear dichroism measurements as function of photon energies. And with this measurement, you can see there's several peaks and wiggles appears. First of all, let's compare the regular absorption measurements. So again, right, in the optical conductivity measurement, what you do is you shine light to a sample, you then measure reflections. So what I show you here is LD. LD is what I measure is the ascending, right, vertical polarized light and the measure reflectivity. Then I also send in horizontal polarized light, measure the reflectivities. Then I take a difference of these two and normalize by the sum. This gives rise my linear dichroism measurements. Okay. So look at this plot where I can already identify, this charge transfer exciton A here, right, give rise this peak in the linear dichroism spectra. Okay. And we can also identify there's a bump we call beta in the literature. So this little bump beta also appears in this little shoulder here. But in the regular optical reflective measurements, optical conductivity measurements, you will see just smooth background and nothing happened. But in our LD spectra, if I zoom in, right, this little shoulder, now I see many wiggles appears, right, a lot of wiggles. And when I see these wiggles, the first response was, well, okay, there could be exciton magneton coupling effects. So we do Fourier transform, and we found that the period of these wiggles is at 28 millieVs. So it's not magneton, because magneton in the nickel phosphate trisulfide is actually 5.5 millieVs, right? So this is not magneton. Then the second possibility is actually exciton phonon coupled together. Therefore, we look at the Raman spectra of these crystals, and here's our measurement. And we don't see any mode at the 28 millieV, but we do see a mode at 32 millieVs, corresponding to outplane motions of these sulfide atoms. Okay, so it's A1G phonons. So now this 32 millieV will be a candidate, right, for these exciton phonon bound states. But why there's a difference? Why it's not the 32? Why we see it's 28? Then we go back to the literature again, okay, and many years ago, right, back to 1968, and this is just a theory paper. So the title paper is Exciton Phonon Bound States, a New Quasi-Particles. So basically, right, we have excitons and optical phonon. We know optical phonon carry dipoles, right? It's polarized. So exciton and optical phonon, they actually form a bound state, and this is called exciton phonon bound state. And the exciton phonon bound state also be calculated, be measured by in many ionic compound, and from empirical and also from calculation. it shows that the binding energy of these exciton phonon bound state is about 10% of the corresponding phonons. So what it means is, right, if you have these exciton phonon bound state and you measure the period, in the spectra, you'll find out the period should be about a 10% less of the corresponding phonon energies, right? So that's exactly what we have. Wait, what we measure here is 28 millieV and the phonon is 32, so it's about a 10% less. So the binding energy basically is 10% of the 32. Okay, so now we can attribute these wiggles to this exciton phonon bound state. And like I say, right, we're not the first one to observe these. It's been done before in different crystals. So, but there's several new features here. The first one is what we see in many different modes, right? These reflects there's a very strong spin lattice coupling effects. And the second is what we can observe these exciton phonon bound states all the way down to a trilayer. In a bilayer, we don't see, I mean, if you use imagination, there might be something, but the trilayer pretty clear, we see some wiggles. So this not being achieved before, because in the past, right, all the exciton phonon bound states see in bulk crystals. And the other new things is here I show you, right, there's temperature dependence of these LD spectra. So you can see, right, these wiggles, what I show you here, the fringes represents the exciton phonon bound states, and they have a strong temperature dependence and they vanish above this new temperature. So what it means is these exciton phonon bound states actually also coupled to this zigzag antiferromagnetic order. And the coupling between these exciton phonon bound state to magnetic order also has not been observed in the past. So this is new. Okay, so in conclusion, right, we observe a highly anisotrophic excitons with narrow PO linewidth in nickel phosphate trisulfide. And the exciton PO has a strong optical anisotropy, which is linear polarized, and we demonstrate it's coming from the zigzag antiferromagnetic orders. And we show this exciton has a strong dependence, right, on the layer thickness, indicates there's electronic structure evolutions as the layer thickness. And lastly, we show there's a very strong spin lattice coupling effects from these exciton phonon bound states. So hopefully I convince you, right? Nickel phosphate trisulfide is a kind of interesting candidate to study the strong coupling between spin, lattice, and the electronic structure degrees freedoms. So any questions actually before I move on to the second part of my talk?
Questions? Actually, I have a question myself. Yes. So when you thin it down from 6 to 7, do you actually know what happened to the magnetic structure of the system, or the Curie temperature, or neo temperature of the system?
Yeah, the neo temperature, when you go very thin, like 3-layer bilayer, it drops a little bit, like a few kelvins. Yeah.
So by monolayer, you still have antiferromagnetism, or you don't?
Monolayer, I cannot make any conclusions.
So it may be actually a non-magnetic.
Maybe yes, maybe not, because the signal noise ratio is not very convincing.
But bilayer, you
bilayer is very convincing. We have it, yes.
Okay.
Monolayer, I will, from my point of view, if you ask me, I will say yes, we have magnetic order, but the data quality is not good enough. Yeah.
To be conclusive. Okay.
That's right. Yeah.
Yeah. Okay, Liang.
Yeah. Thanks for this series, and thanks for the talk. So I have a quick question. Like when the sample is thin, so how do you determine the AB axis, and how do you determine the zigzag direction?
Yeah, that's excellent questions. So we perform these in two ways. One is through the Raman spectroscopies, right? Because the axis of Raman doesn't really change. You always tell, where is the polarization. The second is we also perform X-ray scarings to begin with to identify where these A and B axes.
Yeah. And what about zigzag direction?
Yeah, so that's where they're coming from. You measure these A and B axis, and from neutron scaring, the zigzag is along this particular A axis. Yeah. So basically use X-ray scaring to identify where's your A axis, where's your B axis.
So
for neutron scaring, yeah.
How do you determine the domain problem? How do you solve the domain problem?
That's excellent questions. So when you go really thin, basically there's no domains.
Wow.
Yeah.
Actually, bulk you have domains, but when
that's right.
So it's just naturally in one direction.
Yeah, and if we have a layer thickness difference, then there will be domains. So we also can use this LD to actually image the domain in this structure. I didn't show you guys today, but this excellent question. Yeah.
Yeah.
Oh, yes. I'm just very curious about the nature of these excitons. I think in your result, just from the band structure, they are consistent with Vanyo. So do you comment on this John Rice? Is that just because it's very different, right?
Yeah. So I also talked to the group, and like I say, I don't really understand the resonance axis scarings. So I cannot comment the results, but from my own understanding, spectroscopy wise, if it's a singlet, I will just see one peak. But you can see that in my data, if you pay attention to it, it's not a singlet. I have a structure inside.
Mm-hmm.
And we have a much cleaner data right now showing that inside this peak, actually there's two of them. So if it's a singlet, it should be one peak, but we see multiple peaks. So it's like, okay, so this basically what I was saying is my results are these opposite to the singlet. Yeah. But yeah, like I said, I don't understand the resonant X-ray scaring. So they have evidence to show this downright singlet. Yeah.
Yes, yes. So it's also very, very amazing that this Wanya excitons have such a sharp lines. So is that because the just crystal is super homogeneous, or?
This is another puzzle we have to. So here's what the general thing I can, general features what I can argue is, right? So the Linewidth of the exciton represents, like how noisy your environment is, right? Like basically the phasings, right? That this represents the T2 of the excitons. Then I would argue is when you form these zigzag antiferromagnetic orders, the spin is sort of pinned, and then maybe reduce the fluctuations. That's why the width is narrow. But you can see that when I increase the temperature, right? And that's another plot I have here. The width actually increased dramatically. So of course, I cannot say my width is mainly contributed from the spin fluctuations, because the phonon also contributed in the width. So I cannot say anything conclusive, but at least this give us an indication. The width, might represent some spin fluctuations. Also, this represents from the layer thickness dependence. So the other thing you can see is from layer thickness, when I go to very thin, the width gets really broad. One of the reasons is when you go to really thin layers, and the spin fluctuation gets stronger. So that's another possibility, but that's all speculations, because there could be some other magnetisms, when I go thinner.
That's right, that's right. So maybe the power dependence can tell if how large are these excitons?
Actually, the power, we did that, and we don't see a significant appreciable width dependence. Yeah. Yeah, those are excellent questions. I think we would like to know the answer to.
Okay, that's wonderful. Thanks.
Oh yeah, so I'm really confused. So because your PL intensity when you're showing, it was LDA calculation. It's a functional layer dependence. You said it really matches quite well. Where the correlations are there?
So what I say, I didn't say intensity match, but what I'm trying to say is the trend we observe. So the trend observed here is when I lower when I reduce the layer thickness, right? The PL intensity drops, especially when I go bilayer, drops dramatically by orders magnitude. And with the monolayer, there's no PL observed. Okay, that's number one. Number two is we observe this blue shift of the exciton resonance all the way to bilayers. So that's the two feature observed, right? The PL intensity drops dramatically when I reduce layer numbers. And the second is there's a blue shift. Right. Now we look at the calculations, right? The calculation basically shows is there's two things. The first is when I increase the layer thickness, this peak in this band edge actually lowers down.
I understand that, but I think what I'm confused is that your magnetism does not play any roles in this.
No, magnetism doesn't play a role here. This is just a simple band structure.
Yeah, but your exciton actually couples to phonons and probably some of magnetism. So why the magnetism is completely decoupled in this PL intensity?
Actually, I don't know why it's coupled. Because for me, the intensity here is mainly determined by the electronic structure, either direct or indirect band gap. If it's indirect, how far the band edge away from each other, right? Because if you want to emit a light, you need a phonon to help. If they're really far away from each other, then the chance for them to recombine is harder. Yeah.
Right.
So electronic structure dominates. And the magnetic structure doesn't really change much, from all the way. That's the Prince's question. Yeah.
The spin wave has a very low bandwidth, right? Only 5 millivolt.
The spin wave is 5 milliV. That's right. Yeah.
I see. Yeah. So it's probably the energy scale is so different that they don't couple.
Yeah. Yeah. So we haven't seen exciton magneton coupling effects in this system yet. Yeah.
I see. Okay.
Yeah, thank you. Yeah.
Thank you.
Xiaodong, yeah, continue.
Okay, yeah, thank you guys for all the very good questions. Now we move on to the second part of my talk. So I'm going to discuss these Moiré magnetisms. Okay, so well, I assume the audience know, right? You see all the news in the media. So the twist structure is really interesting and give rise to all sorts of strongly correlated physics, right? From charge ordered insulating states and from topological states and from superconductivities. And so far, most of system we have, right, is focused on graphene or transition metal dicotyledons, etc. All these the crystal basically itself, the parent crystal is non-magnetic. And the question we'd like to ask is, well, what about the Moiré superlattice formed by two-dimensional magnets, right? Anything new we can study there? So that's sort of the motivations, and we use the system we use is that's many kind of 2D magnets. The one we use is CI3, which my group is the most familiar with. So here just a brief introduction of chromium triiodides. In a monolayer, chromium triiodide, if you look from the top, right? These chromium atom form with hexagonal lattice structures, and they form this edge sharing with these iodide atoms, right? Octahedral structures. And the spin is going out of planes. And several years ago, my group performed these magneto-optical co-rotation measurements. So basically, we sent in linear polarized light on a sample, and we look at the polarization rotation of these reflected light. So this rotation angle we call co-rotation angle, theta k. So measure this co-rotation angle as function of a magnetic field in this monolayer. So observe this very clear hysteresis curve. And this is the hallmark of ferromagnetisms with out-of-plane magnetization in these monolayers. And the other interesting feature we observe is, well, as we go to bilayer, and then we look at again, right? See the co-rotation signal actually vanishes for near zero field. And then as a field is larger than a spin flip field, and then we see these strong co-rotation signal appears again, okay? So what we have here is that in the bilayer, right, even though the monolayer is ferromagnetic, but the interlayer coupling is antiferromagnetic. So that's why in the bilayer, we don't have any net magnetic moment at the zero magnetic field. And as the magnetic field is larger than the spin flip field, and all the spin is aligned in the same direction again, then this sort of field induced by ferromagnet. That's why we see this co-rotation come back again. Okay, so this is just a summary, right? Basically, this CI3 is a A-type layered antiferromagnet, and the individual monolayer is ferromagnetic, right? So that's why for the order number layers, we always have these one layer net uncompensated magnetizations. We see a hysteresis loop. As a field increase, we see these spin flip transitions. But for even number layers, the net magnetization vanishes right at the zero field. And then as we increase the field, the spin flip transition happens again. We see these steps, okay? And an interesting property for these van der Waals magnets is actually the interlayer magnetic coupling depends on the stacking orders. So there's quite a few theory work, right, discuss how the interlayer coupling depends on the lattice translations. Here just highlights work from my collaborator D. Xiao, so you can just focus on the bottom panel here. What he shows is energy difference between ferromagnetic to antiferromagnetic as function of the layer translations. So you can see that when you translate the two layers, right, the crystals, and there will be regimes of ferromagnetic states, and there will be stacking corresponding to the antiferromagnetic states. So there's two interesting structure, which is energy nearly degenerate, and one is rhombohedral. This is the structure for bulk crystal at the low temperature, and it appears ferromagnetic. And the other crystal structure is monoclinic. This is structure for low temperature phase for exfoliated crystals, actually. That's why for all the exfoliated crystal we found is antiferromagnetic. It's different from the bulk crystals. It's mainly coming from the structure effects. Now, the question is, well, can we actually control these layer stacking and to control the interlayer coupling? So a few years ago, we used this hydrostatic pressure technique to control the interlayer coupling. So for example, we started with a monolayer, with a bilayer and chromium triiodide, initially with some monoclinic stackings and antiferromagnetic. if I perform these circular dichroism measurements, right, you'll see these typical behavior for monolayer, for bilayer, vanishing, right, circular dichroism near zero field, then after spin flip transitions, the signal will come back. Now we apply pressure and introduce the layer stacking, introduce the change of this layer stacking, right? Then the crystal become rhombohedral. Then we measure this circular dichroism again. You will see that, well, we see this very pronounced hysteresis loop near zero field. So this shows the crystal now becomes ferromagnetic. So this just example shows, right, we are applying these hydrostatic pressures. We introduce this layer slide, then we have these antiferromagnet to ferromagnet transitions. On top, another monolayer chromium triiodide. And naturally, right, there will be local stacking order corresponding to monoclinic. There also will be local stacking order corresponding to the rhombohedral. So without doing anything, you would imagine, right, I'm gonna form a Moiré patterns with part of a sample shows antiferromagnetic and the part of the sample shows antiferromagnetic. There will be domains, basically AFM, FM, and alternating with each other. So this sort of very intuitive understanding, what will be a Moiré magnets look like when you stack two monolayer chromium triiodide on top of each other. So we started with this hypothesis, and we use this tear stack technique. Right, we found this monolayer and pick up part of it, and then stack with very small trace angles. And I'll tell you a little bit more later why we use very small trace angles. And then we measure the circular dichroisms in these twisted samples. So right now the magnetic field is 1 Tesla. So you can see the signal all lights up in the whole samples. And I can perform the measurements at the individual monolayers, right? This monolayer, for example, is very nice, right? Hysteresis curve, just like a monolayer. And I also can measure a natural bilayer, okay, show at the bottom. But if we measure the magnetic circular dichroism signal, MCD, right, at this twisted bilayer, in this twisted bilayer, actually, you will see a non-vanishing MCD signal at the zero field. This resembles a natural monolayer, okay, but it's twisted bilayer, right? But same time, we also see there's a spin flip transition at the higher field than monolayer, but they're consistent with the bilayer. So just by looking at this data itself, basically it tells me, well, I have the twisted bilayer will behave like a mixture of a monolayer and also natural bilayers. So we can perform these MCD mappings at the different magnetic field of samples. So in the middle, I show 0 Tesla, and the bottom I show minus 0.3 Tesla. So minus 0.3 Tesla already is larger than the spin flip field of a monolayer, but smaller than the bilayer. So you can see that for the monolayer, right, the color already changed because of the magnetization flip the directions. But in the middle, the twisted bilayer, it hasn't changed. Okay, so if I take the difference of 1 Tesla and to a 0 Tesla map, if I take difference, then we come up with this map, basically in the middle, this identified as a twisted bilayers. So our data is also consistent with the data from actually Kim Fai Mac and the Jay San's group. They also basically they have the same type of device, and the optical measurements is very consistent with what we have here. So the short conclusion is if you stack a monolayer on top of a monolayer with small twist angle, you'll have a mixture of a monolayer and the bilayer behavior. But the question is, well, what type of magnetic ground states we have, right? And there already a couple of theory work discussed the magnetic patterns for these twisted bilayer CR3. They call Moiré magnetisms. So the image I show you here is from Leon Balance work, and calculate the magnetic patterns in small angle twisted chromium triiodide. So you can see that the orange part represents the strong magnetizations, and it's a ferromagnet. And in the white part, which is zero magnetization, it's antiferromagnet. Basically, you will see these these periodical patterns, right, from AFM to FM. And there's another work from my collaborator Dichroism. He also calculated the very small twist angle chromium triiodide bilayers. And he considered the lattice reconstructions in his models. Then he found, right, this blue, which is AFM, and the red is FM, okay? And then he see these also, magnetic patterns, and at the boundaries, there's magnons, we call 1D magnon, etc. Okay. So without going into the details, right, you will see that there's interesting AFM and FM domain patterns in such a structure. But well, in our measurements, right, you look at what I have, nothing look like what the theory predicts. This main reason is because we're doing these optical measurements, and the laser spot size is limited by diffraction limit on the order of 1 micron scales, but the domain is on the order of 100 nanometer scale. So we don't have enough spatial resolution to tell the magnetic patterns. So we have to find a technique, right, to able to resolve these. So to call for a nanoscale magnetometry to resolve the spatial magnetic patterns. So this technique, first of all, should have enough sensitivities to measure these nanomagnetism. The second is should have a spatial resolution to measure the domain size. And the last one is should not provide any kind of a dynamic feedback to perturb the magnetic states. So the community already provides such a technique, which is called single spin quantum magnetometry. And basically with these MV center, host a single spin, MV center in a diamond. And they have this single spin, which is very sensitive to the magnetizations. And the group led by Malinsky already used these single spin quantum magnetometry to measure the chromium triiodides. So in short, right, they have these trilayers, they have these bilayers, then they perform the spatial mappings. So you can see that the sample mostly homogeneous for the trilayer, right? You see magnetizations, you see straight field map, but the signal actually vanishes for the bilayer because I told you, right, bilayer doesn't have a net moment. They also observe these little tiny, dots, which are defects, right? These defects is on the order of, hundreds of nanometer scales. And so another advantage of this magnetometry is that actually you can provide the quantitative information on the magnetizations in the systems. For example, for individual monolayers, the magnetization is on the order of 15, 16 μb. So we cannot get this information from, for example, magneto-optic Curie effect. But these single spin quantum magnetometry can give us these quantitative measurements. So another work we collaborated with Jörg Retschep group at the University of Stuttgart. We also measured the magnetic domain effects in atomic thin chromium triboride. So this is also bilayer. So in this work, I'm not going into detail. Basically, we measured the domain evolutions as function magnetic field. What we found is that domain actually is pinged by the local defects. So now with the availability of this technique, right now we apply it and to measure the domain patterns in twisted bilayers. Okay, so again, right, I show you the MCD maps, and we focus on this little square here. And what I show you here is a stream magnetic field mapping. You use these single spin quantum magnetometries. This map looks very different, right, from my optical measurements. And again, right, the map I show you here, stream magnetic field. The next one I show you is a reconstructed magnetization map. Okay, so that's a few interesting features, right? The first, you see this little white feature here in the optical MCD imaging. So this little white area actually is a crack during the transfer. So basically, there's a monolayer, and there's a crack of the twisted bilayer. So it's this monolayer. That's why we see this homogeneous magnetization at the 15 μb. Then in this twisted bilayer regime, you see there's a red area which shows ferromagnets, and the white is antiferromagnet. Basically, you see these very disordered look like patterns, right? It's nothing look like a Moiré magnets, just a very disordered pattern, but it indeed a mixture of a ferromagnet and the antiferromagnet. Okay, so we can also perform the measurements at the different magnetic field at the different areas, for example. So one thing you'll notice is when I change my magnetic field, right, from 0.21 Tesla to minus 0.21 Tesla, this is larger than the cohesive field of monolayer. You'll see that the background of monolayer signal already flips, okay? But for the twisted bilayer, most of the part still has the pattern actually doesn't change. And even though the pattern looks like disordered, but actually it's pinged. It's pinged by the local structures in these Moiré patterns, because I told you, right, the interlayer coupling, whether it's magnetic or antiferromagnetic, depends on local stacking orders. So once the sample is fabricated, the structure is determined, then the magnetization pattern actually is fixed. So we cannot change the pattern. Will basically it's locked. It doesn't depend on the field or temperature, etc. For example, right here I show you, we measure about the this is 4 Kelvin, it's 20 Kelvins, and you can see the pattern looks exactly the same from top and bottom. We can also warm up sample and cool down again, the pattern won't change. Okay, so this just represents, right, this the magnetic Moiré pattern actually determined by the stacking Moirés. So now the question is why we don't observe these Moiré effects, but we see these disorder effects. The reason is with that, we know that for these small twist angle samples in TMDs, etc., or graphene, or people already show, right, there's a lattice reconstruction effects and doesn't look like a Moiré. Okay, it's just a couple examples. I'm gonna skip this due to the interest of time. But I would like to mention is for chromium triiodide, actually, it's a really soft material compared to TMDs or graphenes. For example, right, the Young's modulus of graphene is on the order of terapart, but the Young's modulus for these 2D magnets on the order of 30 gigapart. So it's about 30 times weaker. And here also show the data is extracted from this paper. They measured the elastic property of these 2D magnets. So in the middle, they show these deformation factors. So you can see that chromium triiodide, for example, is here. It's easy to deform. But for graphenes, MS2 at the bottom right corner, it's hard to deform. And also, right shows the Young's modulus and also the strength. Strength means how large, right, the strain you need to apply to break the samples. So you can see that BN is here, graphene is here on top. It's really stiff materials and really robust. But for the chromium triiodide, it's still better than plastic, okay? But it's not much, not as stiff and as strong compared to graphenes or MS2. So because the material is much softer, that's why when we stack in small twist angles, then the lattice tends to reconstruct. That's the main reason we don't see the Moirés, okay? Now, can we do better than that, right? So the natural idea is, well, if we use multi-layers, not the monolayer, but the multi-layers stack on top of each other, because multi-layer we expect will be stiffer than the monolayer, and the lattice reconstruction effect will be weaker. So if we go to multi-layer, then there's a possibility we can achieve Moiré patterns. So what type of multi-layer we use, right? For example, can we use a double bilayer? The answer is no. The reason is for bilayers, for example, here's the data we have. We twist a bilayer on top of bilayer. And the bottom is the MCD measurements of a natural bilayer. The top is the MOC measurements of a twisted bilayer. So you can see that indeed, for this twisted bilayer on bilayer, you see there's a little kink here corresponding to the 4 layers, okay? And then in the middle, you see something which resembles the natural bilayers. Okay? And this is just 2 different other samples. So the reason is for bilayer, it's not ideal for studying these Moiré magnetism because we'll look at the bilayer, individual bilayer is antiferromagnet. And if you put two bilayers on top of each other, no, doesn't matter interface is either ferromagnetic coupled or antiferromagnetic coupled, because you put a 0 on top of 0, right? So the net magnetization is always 0. That's why bilayer is not ideal for studying this twisted magnetism. For example, we also use this quantum sensor to image this twisted bilayer. You pretty much just see nothing. Okay. So the next candidate is called trilayer. So for trilayer, we have this. We have 1 layer magnetization which is uncompensated. So for this twisted trilayer, we can equivalently, right? It can be equivalently considered as a monolayer with either spin up or spin down. Now, if we stack a trilayer on top of trilayer with twisted trilayer, now we measure these, the top, right? It's a co-rotation signal of a natural trilayer. And the bottom is a co-rotation signal or MCD of a natural 6 layers. And in the middle is a signal from this twisted trilayer. So you can see that for the twisted trilayer, right? First of all, it resembles signals from these natural 6 layers. See, we have a little bump here, okay? And it also has a signal resembles a 6 layers, also trilayers, like kinks here and here, etc. And with a little signal with a non-vanishing hysteretic loop in the middle. Okay. So next, we perform the same single spin quantum magnetometry on these twisted trilayer on trilayer. The top is a straight magnetic field map, and the bottom is a magnetization map. So now you look at this, it's not as a disorder as we see, right? For twisted bilayer, you start to see some patterns, okay? And of course, right, it's still a little bit disordered, but we can select some areas will look like, well, if you use a little imagination, now it looks like some kind of hexagonal patterns there. Right? The black part represents the antiferromagnet, and the little orange bright color here represents these ferromagnet with magnetization at 30 μb. Okay, exactly equal to 2 non-vanishing magnetizations. So quantitatively, it matches what we expect. So we can also do Fourier transform of these raw data, and the pattern looks a little bit fussy, but again, right, if we just a little imagination, you can see that indeed some kind of hexagonal pattern appear here. So can we do better to understand this data? So we consult with this technique called autocorrelations. So what autocorrelation does is imagine, right, you have a magnetization map called BXY. Then we do autocorrelation of these BXY with a shifted map. We shifted it by delta X, delta Y. Then we do integration of this function, and we get our intensity. So then we can plot these autocorrelation functions as the translation of this map, delta X, delta Y. And then what this pattern what they're gonna do is if there's the pattern is random, then we'll zeros away. If there's some periodic structure in this pattern, then we'll add that up, okay? Or cancel out. And this technique has been used in the past to extract the magnetization information. For example, right, this is the data we took from this PRO paper. So what they use is they use these to simulate these hexagonal domains with disorders. Okay, this is the hexagonal magnetism order, and they have a disorder. Then once they do this autocorrelation, you can reconstruct this hexagonal pattern of magnetic domains. And this is another example, which is a measure the magnetic flux in a high TC superconductor Webby cells. And they also do this autocorrelation function and reconstruct these kind of magnetic patterns in the structures. Okay, so we perform similar measurements or similar data analysis, use these autocorrelations. And on the left, right, is a magnetization map. On the right is these autocorrelations. And we do see disordered, but pretty clear hexagonal patterns. We can also simulate what's the magnetization map gonna look like, right? By consider lattice reconstructions. So this down, and this is just a map we show. You can see that in this calculated map, right, you don't see any fuzziness, which really will organize these hexagonal patterns. Then we can also simulate what is the measurement. Imagine, right, we're gonna use this single spin quantum magnetometry to measure this magnetization map. By considering this spatial resolution and other effects, we can see that the simulation, right, this is what the measurement will look like if we have this magnetization map. So these sort of consistent with our data. And lastly, we can also extract the magnetization in a single unit cells, and it's comparable to what we have from the simulations, etc. So I think we have a pretty convincing results for these twisted trilayer on trilayer. We have these periodical Moiré patterns, which are found by these AFM and also FM. Okay, this is just summary of my talk, and I talked to you 2 examples, shows these spin lattice and also electronic structure coupling. So one is a zigzag antiferromagnet, the other is Moiré magnetisms. And I'd like to thank all the people who did the work and also the funding agencies, etc. Yeah, thank you for your attention.
Very nice talk, Xiaodong. Yeah, it's amazing. The second one, yeah, it's very interesting. So any questions? Yeah, Ximing.
Hi, Professor Xu. Thanks for your talk. I have one question regarding the trilayer, this kind of Moiré pattern, how the domain basically eventually get a review the Moiré pattern. So for the monolayer, you get the Moiré, you get the point that essentially the domain is not movable, actually is pinned by the lattice. But I can imagine for the domain of trilayer Moiré pattern, I think field training might actually plays a role. So I wonder, basically, the question is that do you see any effect of this kind of field training?
No, we don't see any field training effect. So my understanding is in the trilayer, right? All the interlayer coupling, either ferromagnetic or antiferromagnetic, is also coming from the structural effect, right? It's also either it's a rhombohedral stacking or monocular stacking. So it's also pinned by the structure. So actually, I don't expect any training effect.
Oh, so but if for the neighboring domain, for the neighboring layer at the top and at the bottom, if it is antiferromagnet, then initially it will be 0, right? But if you do the field training, then the neighboring, let's say, is a ferromagnetic couple, then the net effect would be, that would be basically ferromagnetic.
I don't understand your argument because the stacking order is fixed. Once you layer down these two layers, say we pick a point here, then this point will be antiferromagnetic coupled. It means it's monoclinic stacking. For example, this point, say it's a antiferromagnetic coupled and it's monocular stacking. So if you want to make it ferromagnetic, you have to change the stacking order.
Oh, I see. Got you.
Yeah, so training cannot do that. Yeah.
I see. Yeah, thanks.
Any other question? So I was curious. I mean, so do you actually know the which? Does it matter which layer? You have 3 layers, right? The antiferromagnetic is one is up down, and then the third one is either pointing up or pointing down. Does it matter which way you put it on top of each other?
It does not matter.
I see.
Yeah.
But I mean, you would expect. I mean, the single layer that's antiferromagnetic would have to transmit exchange coupling, right, to the other 2 layers before it reaches the twisted.
No,
twisted
what
part,
really
right?
matters is the interface, right?
I see.
The interface either ferro or antiferro. Let's give rise this net effect. Yeah. So it doesn't really matter. Yeah.
Okay. Yeah, Hayang?
Yes. So this is really interesting. I wonder if the normal state that is above your critical temperature, is this a Moiré insulator?
I would say no. There's some theoretical predictions that it could be a Moiré insulator, but from my understanding, is probably not a Moiré insulator. Yeah.
So it's not an insulator to begin. Is that metal or is that insulator?
No, it's an insulator, but it's not a Moiré insulator.
How do you know that it's not a Moiré insulator?
Well, I haven't seen any evidence, right? I mean, there are only theoretical predictions. I haven't seen any evidence it's a MOT or not.
It's a D3 compound, right? Chromium iodine.
Yeah.
The layer. So if I just do band theory, it'll be a metal. Even though it's a honeycomb, so probably there's a 2 sublattice, unit cell, but it might be a metal.
Yeah, that's a theory argument.
Right. So then at the normal state, which is above, say, 60 Kelvin or 70 something, if you see an insulator.
It's an insulator, yes.
Yeah. So then one would say it's a Moiré insulator. Then Coulomb interaction or the correlation or Hubbard something is probably large enough. Then your bilayer, the band structure. So then I'm trying to understand what is the correlation effect here.
Yeah, let's say my understanding is no. I don't think there is. Yeah.
I see. Okay.
So because this system itself is the electrons is highly localized in these d orbitals, like you say, right? There's a d orbital chromium. So the electron that carries is highly localized. It's not a mobile. That's the main reason.
That's even better.
It's very poor. It's a very poor insulator. I mean, sorry, it's really an insulator. It's not even a semiconductor. Yeah,
so it's even better then because it's more localized. So you have a more mode physics in it.
But it's different, right? The mode physics is due to the on-site interactions, right? If your on-site interaction it's huge, then yes, you have mode insulator.
Right.
Infinite, right? But I'm not sure. Okay, my understanding is not. I mean, I haven't seen any evidence. It's a mode insulator.
So this is then Slater insulator, which become a magnetic at low temperature. Your magnetism is coming from some Coulomb interaction.
Yeah.
So that means that
it's coming from
correlations for sure.
Oh, sure. Yeah. If you call the exchange interaction as correlation, yes, then it is.
Right. So let me ask a little, probably more realistic questions then. If you raise the temperature and you're this twisting, because in the graphene case, I mean, we do the twisting because the correlation is enhanced by the reducing the bandwidth. So there the correlation becomes showing a superconductivity and so on and so forth. So I'm trying to understand if such a physics can occur in the bilayer or bilayer, some of your fascinating this twisted sample. So if you raise the temperature and then cool it down or something, do you see changes in your magnetism when you have this twisted structure, like a TC grows up or something?
So the TC in a bilayer is indeed is higher, but it's not because of the physics you're talking about, just because of we changed the interlayer couplings.
Yeah, right. So that's just a pop, which is increasing.
It has nothing to do with the bandwidth physics. So the thing is that we started with we start with like I say, it's an insulator, right? It's not it's the electron is highly localized. So if you want to any kind of a band physics as you described.
No, I don't want to band physics. I like the multi-physics here, and I think
no. Okay, listen to me. When I say band physics, means you want the interaction of between layers to modify the wave function of electrons. That's what I mean. So if that's the case, you want the electron wave function is delocalized a little bit, not a highly localized, right? To begin with, in the monolayer. If your electron is highly localized in this in the unit cells or in the chromium atoms, they don't care about the environment. Then the twist angle, the interlayer coupling do nothing to it. Make sense to you? Yeah. So this is the case here. I haven't seen any theoretical predictions say the twist angle will give you a flat band physics whatsoever, because the system itself, if you just look at a bulk crystal chromium triiodide itself, it's already a flat band. But that flat band is trivial because coming from the highly localized electron wave functions.
That's right. So then,
so there's no flat band physics whatsoever here in this particular system. But indeed, if you look at the different system, I think there's some, I don't remember, but there's some predictions in different materials that the possibility of some twist angle physics. Yeah, but not in the system I talked to you today. Yeah.
Right. So then you are not going to get much other than structural effect.
We have a structural effect in terms of interlayer couplings, but another structural effect in terms of electronic properties. Yeah. Right.
You begin with just already. Anyway, I mean, you're already starting from very large limits. So I don't see what's the bilayer other than affecting the antiferro versus the ferro. Then is there a way that you can move or other systems where you can do such physics?
Oh yeah, there's possibility. We're working on it, but I don't. I always say that we don't have any promising results yet. Yeah.
Okay. All right. Okay. Thank you.
Yeah. But I think recently, right, Liang Fu has a theory paper posted online just last week. He has some ideas on how to combine these TMDs with twisted magnets. I show you here, like TMD on top of twisted magnets, and they can realize some flat band physics. Yeah. By Liang Fu, it's a theory work.
Okay.
How you have a question?
Oh yeah, I used to have a question, but I think Xiaodong has already answered. I was thinking about if there is any excitonic effect on these Moiré structures. But seems that it doesn't give extra.
Yeah, probably not. Yeah.
Yeah, thanks.
Okay. Yeah, very nice. Any other question for Xiaodong? Okay, if not, yeah, thank you very much, Xiaodong, for giving this wonderful talk. Yeah.
Well, thank you guys for all the questions.
Oh, Haiyang, oops, sorry. Yeah, thank you.
Okay, I'll log out. Yeah, nice talking to you, Peng.
Yeah, nice talking to you.